All right, you had a worksheet that dealt with vectors again. You can do the vectors, questions, problems you need me to go through, and you would like me to work on for you. Once again, pictures help you out, should help you out immensely as you go through them. Hopefully you can realize as you go through the pictures and draw your pictures in there what you have to deal with, what you have to work with. Everything should revert back to a law of sines and law of cosines for you. Make sure solutions are you have magnitude and also direction. Direction, put it back into bearings. Or if the first four on the front side, when you deal with the first four on the front side, you're looking at the angle formed by the resultant vector and the vector A. Solutions, once again, provided for you. Once again, you have to be self-disciplined to get yourself through these. It's sort of like a college mode in regards to how you deal with homework. And when you get to college, you're going to get homework. You're not going to go through many homework problems from a college professor. These are problems for you to do, for you to have additional practice. If you have any quick questions, we can work with it, but we're going to move on. Like I said, I hope hopefully providing solutions will help you and you can work yourself through it a little bit and try to figure out a little bit better. All right, today we are going to go through our last topic. Sort of a sad day for me. I feel a little tear come to my eye right now. If you need a tissue, you can go get a tissue to dab the tears from your eyes. Because we have seniors, what this will look like for us in this class next week. We'll spend a day of review next week. We will have a quiz. We'll have review day tomorrow, and then we'll have a quiz on Monday. That'll be the last quiz of the 9 weeks. Then Tuesday, Wednesday, we'll be prepped for a final. We'll review for the final. And then Thursday and Friday, we'll do the final in this class of next week. Then the following week, we'll just sort of take off because I want to get the final has to get taken by the seniors. We don't have an allotted time given to us for a final during finals week. So what I do is I just take underclassmen and seniors and we'll take it all on the same day. The following week, we'll have a few days off that you can do what you need to do for other classes at that point. So planning on finals next Thursday and Friday, a week from now, we'll be going through finals. Questions about that? The end is near. All right, today we're going to talk about polar coordinates. When we deal with polar coordinates are a different type of coordinate system. Okay, it is more of a trigonometric coordinate system. What we have done in our math career is we have drawn an x-axis and a y-axis and plotted points by using an ordered pair of x and y. That is what we have done throughout your entire mathematical career. Even when we were dealing with the graphs of trig functions, sine and cosine, we had a y-axis, but then we had a theta axis, and we graphed theta versus y. But we had an axis there that we would hash out and count out by hashing here, and we would plot our ordered pairs wherever we need to plot them. Not everything mathematically is very easy to graph in an XY coordinate system. Some things will be a lot easier to graph in what is called a polar coordinate system. A polar coordinate system is like Spidey's web. Okay, we used to have a graph on the back here on the back chalkboard. It's Spidey's web. If you look at what you have here, you got a spider web right here. Okay, that's a polar coordinate system. You can also think of this as if you would have a globe and you would cut the globe at the equator and flatten out the northern hemisphere. You would have lines of latitude and longitude, and that's what this is sort of like here, lines of latitude and longitude. You could take this and stretch this down over top of a sphere, and you would get the northern hemisphere or the southern hemisphere of a globe. So when you're dealing with polar coordinates, sometimes things will be a little bit easier, and I'll show you here when we do a graph, things that are a little bit easier to graph in a polar coordinate system. If we take a look at this, we have an angle, we have lines that rotate out from this point right here. Okay, these lines we label with our degree measures. And these are spaced out every 15. So I could go 15, 30, 45, 60, 75, 90. Let's see, 120, 150, 180 degrees. This is an east reference rotation, something that we are used to. So these are degree measures of rotation as we go around the middle point there. And once again, traditionally, that's what we have done with respect to our angles of rotation. We have this middle point right here, which is called a pole. Very similar to what you would see once again with the North Pole or the South Pole. That is our pole. Now these circles, by definition of a circle, our definition of a circle that you had back in geometry is a set of coplanar points that are equal distant from a given point. That's your definition of a circle. And once again, mathematically, you can always go back to definitions. So what we have here is this circle here. All these points are equal distance from this given point. All these points here are equal distance from this given point. Well, these are your values that we can also measure a distance away from the pole. So you can label these however you want, but what I will do is I'll skip the first one and say this is a measure of 1, 1.5, this would be a measure of 2, 2.5, and this would be a measure of 3. So this is a distance that we are away from the pole. I could have very easily went 1, 2, 3, 4, 5, 6 if I wanted to. I could do, if I wanted to, if my number's a little bit bigger, 2, 4, 6, 8, 10, 12. It does not matter. It's up to you how you ever want to judge it. If your numbers get bigger, you can go 5, 10, 15, 20, 25, 30. You can do what works for the problem. So when we talk about theta, theta is an angle of rotation, and r is a distance from the pole. We have theta, which is an angle of rotation, and r is a distance that we are away from the pole. And with this, we have an ordered pair. Just like we have x and y, we have r and theta. So r is our distance away from the pole, and theta is the amount of rotation that you have from the 0 axis. Sometimes you'll see this 0 axis. they will call this the polar axis. They will call the 0 axis the polar axis. Sometimes you'll see that term in there. So if we're going to plot some points here, let's plot some points. If we have the ordered pair 230, that means our R value is 2 and our theta value is 30. So if we look at our graph up here, you could do this either way. You can think that I'm going to rotate 30 degrees, then I'm going to go out 2 units. Or you can think about I'm going out 2 units and I rotate 30 degrees. Once again, you can think about it either way. Just like you plot the ordered pair x, y, you can go out left and right x and then go vertically y, up and down. Or if you wanted to, you could go vertically up and down y first and then left and right x. So this would be the ordered pair 2 and 30. Go ahead and plot these other ordered pairs down here. And label them with an ordered pair. Check your plots with somebody around you. Okay, the first two should be fairly easy for you. It's not very difficult plotting ordered pairs. The last one is a little bit more of a challenge because we have to try to figure out what is meant by the ordered pair -3 and 300. Well, let's take a look. If I plotted the ordered pair 3 and 300, that means I'm going to rotate all the way around the 300 and go out 3 units. So this would be the ordered pair 3 and 300. I go out 3 units on my line of 300 degrees. Okay, that's easy. But the question is, what happens when we throw the negative in there? Well, mathematically, once again, we could say this is a -3, or we could say this is the opposite of 3. The opposite of 3. Well, let's look what happens. If I had to order pair 3, 1, I would go out from my origin 3 units to the left, to the right, and then up the value of 1. But then if I would go -3 and 1, which direction would we have to go? Yeah, the opposite direction. So we would have to go the opposite of 3. 3 takes us to the right. Negative takes us to the opposite of 3. So we go out to -3, then we go upwards. That's the same method of madness we had to think about here. If I would go to 3 and 300, it would take me out to this point right here. If I go -3, 300, what should we do? Where should we go? How do we go the opposite of the +3? Well, which line would we go out?
On the 120.
The 120 line. Think of having an axis here. Think of having an axis here. If I go out the 300 axis, but I go opposite to the 300. Well, here is my line that is the 300 axis. If I would go out the line that's opposite that, that's going to take me out the 120-degree axis. So it's going to take me back to this point right here, where we have 3 and 120. This is also the same point as -3 and 300. So we just go the opposite direction. So let's take a look at getting a graph down. Once again, let's label our axes. And let's label our circles. We'll still keep it 1, 2, and 3. And what we want to plot is we want to plot the r equals 1 plus cosine or 2 cosine theta. Well, just like when we initially started graphing y equals x plus 2 in the algebraic system, we made a little chart of x and y. We had values of x, we subbed values of x in and solved for the value of y. And then we created ordered pairs. When we graph in the polar coordinate system, we have to follow the same method of madness. So we have r is equal to 1 plus 2 cosine theta. We have these values of theta that we can plug in here. We can choose whatever values we want. But I just want 0, 30, 60, 90, and so on. So what I want you to do is plug in 1 plus 2 cosine 0, 1 plus 2 cosine 30, 1 plus 2 cosine 60. Get a decimal value here. That will create an ordered pair of r theta for you. I want you to plot those ordered pairs. So find your values of r. Find your values of r. Check those answers with somebody around you. And then plot the ordered pairs that you have. And going to one decimal place is fine. You're going to get decimals. You're going to get 2.72. Just go 2.7. So just click to your calculator. 1 plus 2 cosine 0, 1 plus 2 cosine 30, 1 plus 2 cosine 60, 1 plus 2 cosine 90. Okay, then plot your ordered pairs. Do not connect the dots though. Once you find the values, plot those ordered pairs. Once again, do not connect the dots yet. Just plot the ordered pairs. You don't have to. It makes it awful messy. Because we're going to eventually connect the dots again. You don't have to write the ordered pairs in there because we're going to connect the dots. If you write the ordered pairs, stay outside the graph, the middle of the graph. All right, we take a look at our R values. Maddie, what do you have for our R values here? Just read down the column.
3, 2.7, 2, 1, 0, -0.7. -1, -0.7, 0, 1, 2, 2.73.
All right, so we go to our graph here. At the value of 0, we're at a value of 3. At a value of 30, we are at 2.7. At 60, we are at a value of 2. At 90, we are at a value of 1. At 120, we are at 0, so we're at the pole. At 150, we're at -0.7. So at the 150 line, we have to go back 0.7 into here. At 180, we have to go -1, so we are here. Let's shoot 210, we are at -0.7, so we are at the 30 line. Then we're back to 0 here. At 240, 270, we are at 1. So 270, we are at 1 here. At 300, we are at 2. At 330, we are at 2.7. And 360, which is the same as 0, we're back at 3. Okay, so we got a bunch of dots here. The question is, how do we connect them? Well, the nice thing about what polar coordinates will do for us is it allows us to be able to graph things that are in more of a curved nature and a little bit easier in a curved nature in regards to dealing with the equation. How do we connect the points? Well, how we connect the points is we go in order of our degree measure. So we're going to go 0, 30, 60, 90, 120, and so on. And this is going to be a curve, so you don't need a straight edge to go from point to point. You're going to curve and curve all the way to this point right here. So we have a curve. At this point here, we will loop and back around again. And then we'll follow our curve back out and around, and we will get back to our point again. Okay, once again, you do not need a straight edge for this. It is a curved line as best as possible. This picture is called a limacon, but it also has a loop. So you have a limacon with a loop. You also have limacons without the loop. You have cardioids, you have 3- and 4-leaved roses, you have different systems that you have in regards to pictures you have. A lot of the old school pictures, computer pictures, a lot of old school computer pictures and like pictures of people on a screen, a computer generated screen, used to be all done with polar coordinates. The reason why is this equation is not very difficult to deal with. But if I would change this into an XY coordinate system, give me a second. Let's see, we have x over r squared is 2x, x squared plus y squared. So what you have here is in an XY coordinate system, this would be your equation in an XY coordinate system, which means you would have to substitute values of x in and solve for the values of y, which is a little bit more complicated than subbing in values of theta and solving for r. It was fairly easy for you to plug in 0, 30, 60, 90 into 1 plus 2 cosine theta. But if I substituted the value of 1 in for here, or the value of 2 in here for x, and solve, we would have the value of 4 plus y squared minus 4, all being squared is equal to 4 plus y squared. We would have to solve this all for the value of y, okay, which is a little bit more difficult than plugging in values of theta and solving for r. So once again, a lot of computer-generated diagrams were generated with polar coordinates. If you ever play any old school video games, Tecmo is one that is kicked out in my mind because they had images of people playing football, or the old school baseball. They had images of people playing baseball. They were all computer generated, but computer generated with the idea of polar coordinates. That's how the pictures got there. Now your homework for tonight is on page 273, 1 to 8, and then the rest of them, 9 through 21, some various problems in there. Those are just graphs. Now, what you're able to do is problems 1 to 8, you're just plotting points. So you can pick one of these graphs here and just plot the points on the graph and just label them. When you go down to problems 9, 11, 13, 16, 21, that's doing what we just did here. Now, they also have names of things that you'll be graphing. When you get to a 3 lead, when you get to the 3 leads and 4 leads rows, your values of theta that you want to substitute in, you're going to want to substitute in some intermediate values here. But then you'll be able to stop at 180. So it's going to be the same number of points, but you're going to want to go 0, 50, 30, 45, 60, all the way up to 180. The reason why is when you do your graphs, you have a point here. For the 3 lead rows, you're going to go to a point here. You're going to come back to here. You're going to go to here, back to here, here, back to here. And you'll just continue this pattern over and over again because trigonometric functions are periodic functions. When you throw in the 15s in there, what will happen is that will give you an intermediate values that are here, here, and here. So then you can complete, say, your 3 lead rows. Okay, so when you have the 3 lead and 4 lead rows, you're going to have the same number of points. You just want to use the 15s in there. When you have the ones at the beginning, you can go 0 to 360 and be done with it. Graph paper here is provided for you, so you don't have to draw all the graphs. And on the test, the graph paper will be provided for you also. All right, what question do you have? Dookie.